Alrighty, welcome to this episode of Lectures with Liddington, and today we're going to talk about the wild world of water. Last episode we talked about chemical bonding, and we are going to talk about how that works specifically with water, because water is pretty wild. When it comes to the properties of water, it's really, really unique. And the reason is because water is polar, and that means that it is charged because of an uneven distribution of electrons. So what this means is that as those electrons are swirling around in those different atoms, they're not spending time in the same places the same amount of time. So what happens is you end up with your electrons spending way more time hanging out in this oxygen. So you end up with a slightly negative charge here. That symbol means slightly. A slightly negative charge on that oxygen. And then because it's slightly negative over here, you end up with slightly positive over here on your hydrogens. Now, this uneven distribution is what leads to all the cool properties. This is why you end up with hydrogen bonding. So, hydrogen bonds are that attraction of the slightly positive hydrogen to the slightly negative oxygen. So then you'll end up with this attraction here. We've got this slightly positive here, slightly negative here, slightly positive, slightly positive, slightly positive, slightly negative, slightly, that's not very proportion, slightly negative, slightly positive, and slightly positive over here. So notice we've got our slight negative and our slight positive. Opposites attract. Paula Abdul taught us that, right? So those are attracted to each other. And then over here, the slight negative and slight positive are attracted to each other. And then that slight attraction is actually a pretty solid attraction. Hydrogen bonds are pretty strong comparatively to van der Waals forces, in that they really do, those water molecules really just want to hang out together. And that hanging out together, that's cohesion. So cohesion, this is water molecules. Molecules. Oh, well, I guess it doesn't let me do an eraser. Oops. This is water molecules. Let's try again. Molecules attracted to each other. So, one water molecule and another molecule, they are attracted to each other. So you end up with this beating together of water molecules. That's why you get the beating on surfaces, like the hood of your car, the water's kind of beads up, or on leaves of plants, that water beads up, is because those water molecules, they want to be friends, they're attracted to each other, they want to pull in towards each other, and you'll see those little beating on those surfaces. Now, water is also adhesive, and that is adhesion, which is water molecules attracted to other surfaces. Or other molecules. So an example would be here in this graduated cylinder. Notice there's a curve here. We call that a meniscus, in that the water, it's not flat, right? When you read that graduated cylinder, you've got to look at the fact that the water is curved. And what's happening is the water is sort of climbing up the edge of the glass or the plastic, depending on what kind of graduated cylinder you have. That water is sort of climbing up because it is attracted to the edges of that material. Now, you do get this nifty thing called capillary action. And capillary action is the combination of cohesion and adhesion working together. And that's to take water up. Now, examples of this would be plants, right? So a sunflower over here, really, really, really tall, right? And gravity is kind of really important and brings everything down. So a tall plant like a sunflower has to work really hard to get water up against that force of gravity. So what it does is it takes advantage of capillary action, the cohesion of the water molecules being pulled together, and then the water molecules along the edges of the inside of this tissue, this water-moving tissue, it's called xylem, this water-moving tissue inside the plant, it'll move up the edges. So just from cohesion and adhesion working together, the water will actually travel up the plant without it really doing any work. It's just taking advantage of water and its cool properties. Another example is if you have ever taken your straw and put it in a cup of water and then stick your finger on it and then pull it back up, you have just illustrated capillary action. Another really nifty property of water is that it has a high specific heat, and specific heat is the amount of energy needed to raise the temperature of a material. So specifically here, we're talking about water, but it has a high specific heat, which means it takes lots of energy to raise the temperature of water. This is why a watch pot never boils. If you stand there just waiting for your water to boil so you can make your noodles, well, it's going to take a while because water has a high specific heat. That those hydrogen bonds keeping those molecules together makes it really hard to get them apart so that it can boil off. Same thing happens with the ocean, right? So if you've ever gone to the beach really early on in the season, you'll notice that it's really cold. Well, it's because it also takes a really long time to heat it up, right? The ocean's really, 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 really big, and it's really hard to raise the temperature of water. It takes a lot of energy, so it takes a lot of time. So early on in the season, you'll go, it might be really warm, but that water won't be warm. Same thing if you go at the end of the season, or not same thing, opposite. Opposite if you go at the end of the season is that it's going to be warmer, feel warmer, because it hasn't lost that heat yet. It works in both directions. So let's take a look at some examples of this in action.